which is about orthogonality. And the first thing in this section is actually the definition. What do we actually mean if we say two vectors are orthogonal? So that's always a good thing. So we know actually what this is about. And it's very basic. It just says if you have two vectors, u and v in Rn, then we say u and v are orthogonal. Which is kind of another word for perpendicular, at least in this setting. If the dot product is 0. No? And keep in mind, remember, the dot product is norm u times norm v times cosine, and the cosine is 0 if the angle is 90 degrees. So this essentially means that the angle between the two vectors is 90 degrees. No? So that's what it means. Also, according to this definition, actually the 0 vector is orthogonal to every other vector, because if you multiply by the 0 vector, it's automatically 0. But that's kind of a special case, and it doesn't mean too much. No? Also, you should think about non-zero vectors here. But formally, it's orthogonal because the dot product is 0. No? Okay, and now the first thing in section 3.1 is actually that we connect now this orthogonality to the first day of class when we talked about linear equation systems, and we saw that each row in a linear equation system is actually a line or a plane. And now we are coming actually back to this, but we look at it in a different way. So essentially, these coefficients of the linear equation system mean something. Okay, so, and I hope it's a little bit hard to organize this. I hope it becomes clear at the end what we are doing here. So let's do this like this. So for vector n in R2, so n is a vector in the plane. So n itself has two components, and we assume that n is not the 0 vector. We look at all vectors. Let's call the vectors W, such that W times n is equal to 0. So I make a picture for this. So now let's say I just make up a W, for example, an n, sorry. For example, this guy is n. And now we take all the vectors that are perpendicular, have a 90-degree angle. So we see all these vectors. Also when I make the line, it means from the origin to here, from the origin to here. So every vector where the end point of the vector is along this line is perpendicular to n. So this line I call n, L. So, and the point is this line is perpendicular to the vector n. So if I look at all vectors W such that W times n is 0, then the result is actually a line through the origin perpendicular to n. Okay, so this is, and I like to call this star. So now the next thing would be, what about if you make P, which is all W, so maybe I should first say that my n has changed. Now if n is not in R2, but in 3 dimensions, if n is a vector in 3 dimensions, and n is not the 0 vector in 3 dimensions, and we look at the same thing, take all three vectors, also vectors with three components, such that Wn is equal to 0. Let's call this guy plus. Then P. Now, you think about in 3 dimensions, I have a vector. Let's assume this here is n, my vector n. Then it turns out if you look for all vectors which are perpendicular to one vector, you don't not just get a line, but many lines, because there are many lines which are perpendicular to this vector in 3 dimensions. And it turns out, let's take this guy here, what you get is actually a plane. Every vector in this plane is perpendicular to this vector. So in 3 dimensions, if you look at all w's that are perpendicular to n, this is actually a plane. And the plane is perpendicular or orthogonal to n. So again, if we look at all vectors that are perpendicular to n in 2 dimensions, we get L. L is a line. If we look at all vectors which are perpendicular to a vector n in 3 coordinates, we get a plane. And the plane is perpendicular to this vector. Okay, so now we extend this, because here I said, how do I get the line? I take all possible vectors that start in the origin and are perpendicular. No, there are infinitely many in this direction and infinitely many in this direction. And if I put all these vectors together, I get a continuous line. Now, instead of starting at the origin, we can say, why not start somewhere in the plane? Okay, and that's the next step. So now, instead of having just one vector to which we are perpendicular, we move our starting point to an arbitrary other point, not to the origin, in the plane. And this point I call Q. So now, given n in R2, again, n not the 0 vector, and Q a point, now we're looking at the plane. Let's say here is the point Q. Then in this point Q, I try to make the same vector we had before, n. I mean, it's not important that's the same, but for this example, I like to make it the same. And now we look for, first I write it down as a formula. L is all points in the plane such that when you go from Q to this point, so QW, such that this connecting vector is perpendicular to n. So the dot product is 0. So again, when you think about it, for example, this point works, no? Because when you connect these, it's perpendicular. And now you can say, okay, why this? Why not this, or this, or this, or this, or this? And the same thing in this direction. So it turns out what you get, again, is all points on a line, which goes through the point Q and is perpendicular to n. So again, maybe this time I write it in words, is a line perpendicular to n and through the point Q. And now you can imagine you can do the same thing in 3 dimensions. In 3 dimensions, or in the 3 space, you can take a point and a normal vector. But this time, this point is not the origin. You move it to another point. So then this point would be your center, and this is your normal vector. And then you have a plane in space going through this point perpendicular to n. So again, if you have Q in R3, N in R3, where this is kind of confusing a little bit. So this is a point, this is a vector. No? But you can always identify a point with a vector, at least for our purpose, because a point is always given by a vector from the origin to the point. So for us, it's actually not a big thing to mix this up. In general, it is. And then P is all QW such that QW times N is equal to 0. And that's a plane perpendicular to N through the point Q. And just, sorry, I just saw something I should not write. QW, I should just write W here. No? So these are all W such that the connection between Q and W is perpendicular. Same thing here. Sorry, I messed this up. Okay, so, and like I call this star and this plus, I call this here star star, and this here the plane plus plus. Okay, why do I do this? So now we know this is the equation of a plane through the origin perpendicular to N. Sorry, a line. This is the equation of a plane perpendicular to N through the origin. That's the same thing. Instead of going through the origin to Q. Now each of these equations or definitions of lines and planes, we like to translate into an equation. So what kind of equation is this? 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 So let's do first the homogeneous ones. So let's say, can I do this? Let's say, make it here in R2. I like to have everything together so it's easier to compare. You see actually the similarity. I'm not sure if this works out. So let's do first R2. And now for the vector N, I assume it has two components, A, B. And the vector W has components X and Y. So now the equation star is 0 equal to W times N is equal to, now we do the dot products, A times X plus B times Y. So, and now we are really back to the first day of class when we talked about equations in two variables homogeneous. So it turns out the equation of a line through the origin is a homogeneous linear equation. But now, so what did we gain out of this, out of the introduction of the dot product? It turns out now we know the two coefficients of a linear equation system are actually the coefficient of a normal vector. So these numbers actually have a meaning. They tell us there is a vector which is perpendicular to this line. Okay, so this would be, again, this is here 2-dimension. That would be the equation of a line in two components with normal vector AB. Now we go to the equation when we shift it. So we go to this equation. Now we have an additional point x0, y0. So, and how do we calculate Q to W? How do we calculate the connecting vector? So here we have Q has components x0 and y0. And now the vector from Q to W is from here to here, I have to subtract the components. Is x minus x0, y minus y0. So this equation here becomes 0 is equal to A times x minus x0 plus B times y minus y0. Now I sort this out, A times x, B times y. And then I do minus ax0 minus by0. So I write this as minus ax0 minus by0. And we see this together is just a constant because a normal vector and the point is given. So this is just a constant. I call this constant now d, because later on there will be component c here. So we have 0 equal to a times x plus b times y plus d, and you can bring the d also to the other side as minus d. So this again is in two components in R2, the equation of a line which is perpendicular to the vector AB and goes through the point Q. So again, that means an inhomogeneous equation in 2 dimensions is always the equation of a line. Again, that goes back to the first day of class. Now we do the same thing in 3 dimensions. Here, my normal vector has actually 3 components. Again, it should not be the 0 vector. So A, B, C, at least one of them has to be non-zero. And W I call X, Y, C. Then the equation, the homogeneous equation, plus, so that's the equation of a plane through the region, is 0 equal to W times N, which is now A times X plus B times Y plus C times C. Okay, and again, we see now the only difference to kind of the first or second day of class is when I told you already this is the equation of a plane in 3 dimensions, also in 3 coordinates. The only difference, suddenly A, B, C get a meaning. So A, B, C are not just arbitrary numbers. They give you a vector which is perpendicular to your plane. So this has now a geometrical meaning. And I like to make now the case plus plus short. So now we have also a point Q. So the plane actually goes to the point Q. So I make plus plus. So what about, plus plus. So what about the equation of a plane through the point Q? So the point Q has now components x0, y0, and c0. Then the equation is 0 equal to a times x minus x0 plus b times y minus y0 plus c times c minus c0. And I can sort this out. A times x plus b times y, again here's 0, plus c times c. And then actually everything else is minus ax0 minus by0 minus cc0. And again, I call this guy here d. So we have this is the equation of a plane with normal vector ABC, which goes through the point Q. So the Q determines what number the D is. So the D here and the D here always comes from the point which you pick. Keep in mind, by looking at the picture, you can pick also other points. So the point is not, it's not just one point. Usually they give you, oh, this is the point. But if you go the other way around and you say someone shows you a picture of a line, you can actually pick any point on the line. No? So the point is not unique to a line, but if someone gives you a point, it determines the line. No? So from point to line, that's unique. From line to point, that's not unique. Okay, so the whole point is now we understand a little bit better what these linear equations actually mean. Also here, homogeneous is a line or plane through the region. Non-homogeneous, it's a line or plane going not through the region, but through a certain set of points as a starting point. No? Okay, and for sure now you can say, why do we stop at R3? Only because if you make more and more components, it's harder to imagine what happens, but it turns out it's actually the same. No? So if you have a homogeneous equation with 4 components that is in the 4 coordinate space R4, again a plane through the origin, where the plane now itself has 3 coordinates. So it's what we call a hyperplane. And the same thing in the moment you add a constant, the hyperplane is shifted away from the origin.
Professor?
Yeah?
Over by the first plus right there, on the R3 side, is that W times U or is that W times N?
Oh, it's N. Sorry, there is no U here.
Okay, I was just making sure. I was like,
they're just very good. My N's are always terrible. Also, it's an N, yeah. Also, I originally I had actually U times W, but I said, oh, that's really bad because there's a U and an N. So there's only an N here, no U. No?
Okay, thank you. I was
Sorry,
just
yeah.
that.
Okay, so the point is now when you think about it, what it actually means after having the inner product or the dot product, we understand a little bit how to interpret an equation. So we see, oh, these coefficients are actually coefficients of a normal vector. Okay, and this result, what we just derived, is in your book, Theorem 3.3.1. And is it okay I move on to the next page?
Yeah, you're good.
Okay, so these 2 results, or at least I think the inhomogeneous, that in your book, when you look there is theorem 3.31. So that's what we just derived. So